Hardware to Save a Planet explores the technical innovations that are giving us hope in the fight against climate change. Each episode focuses on a specific climate challenge and explores an emerging physical technology solution with the person bringing it into reality. I'm your host, Dylan Garrett. Hello and welcome to Hardware to Save a Planet. I have here Silvain Toromanoff joining me today from Germany. Silvain is the CTO and co-founder of NeoCarbon, a direct air capture or DAC company with a promising approach. In the world of carbon removal, DAC is getting a lot of support and interest because it should be scalable, easy to measure and verify, and can have high permanence if the CO2 is stored underground. But there are trade-offs in that it requires a lot of energy and a lot of new expensive equipment and infrastructure. I think Silvain and NeoCarbon have an approach that could address those challenges, and I'm really excited to learn more about it. Silvain is an engineer who quit his job just a couple of years ago to focus on building something to address climate change, and it's really impressive to see what he has done in the short time since. I think he's setting a good example for a lot of us who are probably also feeling that pull to jump in and do something. Silvain, it's an honor to have you on the show. Thanks for joining.
No, hi. It's an honor for me. I'm super happy to be here and excited about this conversation we're going to have. So thanks a lot for having me.
Great. Yeah, me too. So you're actually my first guest from Germany. I know you're not originally from Germany, but you live in Germany currently. What's the climate tech scene like there? Are there a lot of startups, a lot of new innovation, funding, academic research? What's it like over there?
Well, so we started NeoCarbon in Berlin, where the company is based and where I live today. And it's definitely been a really growing hub for innovation and startups. So it's actually been pretty crazy, I would say, in the last 10 years. So Berlin has changed. Of course, I wasn't living there back then, but Europe is, especially for US people, I think it's quite tiny. So I had the chance to go to Berlin many times before I moved there. And it's just a completely different vibe at this point. So yeah, on the tech scene, it's been really, really good. I would say that's also one of the reasons we actually decided to be in Berlin. And also because, for example, our first investors, Antler, a venture capital company, basically runs this program and to kind of bring founders together. And this is what we did to meet with René, my co-founder and the CEO of NeoCarbon. So they definitely have a lot of infrastructure in Berlin around funding, around building a company innovation. Even public funding is also quite good. So definitely great. On the climate tech scene, it's still pretty good, I would say, as well. Unfortunately, the entrepreneurship scene is still mostly not climate tech. Unfortunately, a lot of people are still not switched their focus to what I consider more important things. But for sure, Germany, I think, has always also had a mindset for green and sustainability. I think so I'm originally French, actually. So even growing up, we always heard about how green Germany was. And well, it's a bit more controversial these days. But for example, they did shut down their nuclear plants for kind of green reasons. So there's a lot of green politics, at least always at play in Germany. And of course, then impacts the amount of, for example, public funding we can access with NeoCarbon based on German government funds and even Berlin funds. Yeah, so I would say that's roughly it around Berlin, and it's definitely been a very good for us, a very good decision to kind of go there and stay there for the company.
Awesome. And you're somebody who made that switch pretty recently, as I understand it. Can you talk a little bit about what you were doing before NeoCarbon and what your motivation was to quit and do this?
Absolutely. It's definitely been a very big decision, but also a very kind of important and almost mandatory decision for me in the end. So I'm an engineer, as you said. I grew up in a very kind of sustainability-focused family, but my journey was still like everybody else's. 20 years ago, we didn't talk about sustainability like we did today. You had advices don't let the rudder run or turn off your lights, but it wasn't very quantified. It wasn't very organized. So that has changed a lot. And of course, that and the kind of talk and coverage that came with it, plus the fact that just opening your eyes in these recent years, I could get more and more anxious about, okay, where are we going? That kind of really drove me to, I really want to do something. So before NeoCarbon, I was actually working in Finland in a second startup I also had, also as CTO, but it was a software company, so very unrelated to climate. And actually, we were kind of e-commerce company. So I was more or less joking the whole time that I was helping people buy stuff they don't need. And eventually I was just thinking okay, this is just not actually a joke. I should really do something I care about. I was already kind of doing everything I could on my personal life to try and mitigate my own impact. And I just realized at some point, well, I tend to work a lot, I would say, especially in these recent years when I had like more like own startups. And I was like, okay, it would make sense that I also commit my professional life. So I think it was a very rational decision in the sense that, again, being an engineer, I try to quantify, okay, what can I do with my time? What can I do with what kind of impact can I have with my life? And this was just a natural switch. Like, I need to do something better. What I'm doing now doesn't really suit my values. And the rest kind of was like logically following.
And how did you zero in on direct air capture?
Also an interesting story. So basically, when I quit my previous company, it took a while. I was CTO there, and there was a lot of things to pass on before I could go. So I was actually very vocal already then in the, like, let's say 6-9 months it took for me to really get out, that I'm going to do something next, and it's going to be around climate, because that's obviously, as I just said, the drive for me to leave in the first place. So I started kind of gathering all kinds of information around, okay, what kind of structure would make sense, what kind of topic would make sense, and so on. And carbon capture was definitely one of the top of my list, because it's kind of grouped this triptych of things that I've always thought would make sense for me from the impact perspective. So those will be, it needs to be exciting to me, because I know myself and I can only be productive if I'm excited about things. So it needed to be an exciting topic. Of course, it needed to be an impactful topic, because otherwise, what's the point? And third one, it also needed to be a scalable topic. So specifically in today's world, that meant more like a profitable business. I considered for a while kind of looking at more like NGOs or nonprofits or even politics. But yeah, again, that didn't fit too much the exciting part as well. So that kind of narrowed down again pretty quickly on startups and then profitable business models. But it was still at that point, like I couldn't find my angle. Like I was just like, okay, carbon capture and especially direct air capture is super exciting. It's a really difficult technical challenge nobody has really solved. It would solve a lot of problems if somebody actually figured it out. And it definitely has a potential to become a large, very large kind of industry. But I was just like, okay, I'm not a chemist. I'm an engineer, yes, but I'm not like at all the guy that has the super new idea that will cut the cost by 10. So for a while, it was actually on the shelf there. And it's only when I met René, and he has exactly the same experience. So before we met, he was also looking into direct air capture. He even went to the Climeworks Direct Air Capture Summit the summer before we met. And he really had the same kind of, I don't know what's my angle. And it's only when we started talking together and we started looking around, we found actually inspiration from this company called Noya in the US, which nowadays has actually pivoted away from this. And even very early on, of course, with different industries and different markets, we had quite different technologies. But yeah, they also kind of looked at cooling towers and retrofitting for doing direct air capture. And this is when René, who's also just like me, recently more from the startup background, realized that, hey, in this approach, at least initially, we could do something with less funding. Like you don't need to build like a 10 million plant to prove your point. And also much quicker. And it's the savings come initially, at least from the execution and the scaling part, and not like really the deep tech innovation. So you will still need to deep tech and will need to kind of improve the tech over time. But you could still at least start with something a lot more kind of, purely on the retrofit part, on the quick execution. And these are things that both me and René, we were pretty familiar and confident in. And that's how we found our angle. That's how we were like, okay, let's try this and build a company around this. And of course, I would say it's been going quite well since then. It was already 18 months ago.
So you mentioned you're using cooling towers. Can you kind of fill out the description of what your solution is?
Yeah. So in principle, cooling towers, before I go into our solution, is something that if you think about anything, you're going to think about like the nuclear power plants cooling towers, those big kind of chimneys, which actually are not chimneys. They're virtually just big kind of machines that blow through a lot of ambient air. So they don't actually reject air. They take ambient air that's typically cold and dry, and then they cool stuff down, typically water, and then they reject kind of hotter air and more humid air. So that's basically what they do. They just take a lot of ambient air and they take some heat from somewhere else. So in the case of a nuclear power plant, from the power plant, and then kind of they reject it out they blow it up in the atmosphere, basically.
These are you're describing kind of these big cylindrical, massive towers that always have steam coming out the top.
Exactly. And the point is, those are the ones that you might kind of course, have seen. But what basically very few people know is that cooling towers are actually virtually in every industry. So of course, those are the massive ones that you can see from far away. But in practice, it's basically in every industry. So you have it in like food processing, you have it in metal industry, you have it in the chemical industry, different scales. And of course, when they get smaller, they look more like basically boxes with a fan on top instead of like very, very big towers, but they're still called cooling towers. And they even go all the way down, especially in the US, where the AC systems, the cooling systems for more like offices and, for example, shopping malls are still pretty large. Then you also have them on top of buildings as well, even in cities. So if you take a helicopter view of, for example, Manhattan, you will see cooling towers everywhere. Like you can recognize them pretty well once you know what to look for, those kind of repetitive black fans that are pointing towards the top. So this is kind of like the basis. Like cooling towers are everywhere. And what they do is they process a lot of ambient air and they evacuate a lot of heat. And that's extremely interesting for us because when you look at direct air capture, one of the biggest challenges, okay, it's too expensive. And why is that? Well, primarily because the CO2 in the air you breathe, in the ambient air, in the atmosphere, even though it's terrible for the planet, it's actually only about 0.04%. So it's extremely dilute. It's very, very little amount of CO2 in the air in absolute terms. And that means that if you want to remove billions of tons, which is what we have to do, unfortunately, at this point, in the next decades and all the way even to 2100, you need to process this insane amount of air. So that's one thing. You need really a lot of air, and you also need a lot of heat. So the process itself is very energy intensive, as you mentioned at the very beginning of the podcast. And that's mostly based on the heat you need during the process. So I don't think we have to go right now, at least in the chemical process that goes into direct air capture. But let's say at some point, you need a really big amount of energy, typically in the form of heat, to kind of process your CO2 and be able to kind of continue your capture. And in this case, again, cooling tower, their whole job is somebody has heat they don't want, and they just blow it. And they're paying somebody, they're paying the cooling tower manufacturer, they're paying for the electricity of the fans of the cooling towers to kind of evacuate it. And what we say is, hey guys, that heat, actually, we could leverage it to do carbon capture. We actually could take it off your hands pretty much for free. So we just build a little machine there next to your cooling tower. It's basically not going to impact negatively, at least. It might even have a positive impact on the performance of your cooling tower, but mostly at least it's transparent to you. And what's going to happen is that now instead of blowing all that heat in the atmosphere, a lot of it will be used for doing carbon capture. So suddenly you're kind of tapping into these underutilized streams that are not very or big interest to anybody right now. And in exchange for this, as a cooling tower manufacturer, or as a cooling tower owner, you get basically like carbon emission reduction. So that's just a win-win.
Yeah. So you're talking about how kind of energy intensive the process is. I was trying to figure out how to quantify this earlier, and I saw that it was from MIT. The MIT Energy Initiative says it can take around 1,200 kilowatt hours of energy to capture 1 ton of CO2 in a typical DAC process. And I mean, just to put that in perspective, that's something like 1 or 2 homes worth of energy per month that an average home uses in a month. So if we have to do 1 billion tons of CO2 per year, we're talking about a crazy amount of energy if we're using kind of a typical DAC process. So I guess a couple of questions for you is that, do you look at it in terms of kilowatt hours per ton removed? And are those numbers kind of in line with your understanding? And do you have a sense for how different your approach could be? And then also, it sounds like you're able to use the waste heat. So you're taking out part of the energy demand, which is the heat used to kind of regenerate your sorbent, which is capturing the CO2. How much of the total energy budget is heat versus the energy to blow the air through your reactors?
Yeah. So on the first part of the question, actually, I would say 1,200 kilowatt hours or 1.2 megawatt hour per ton is actually very, very good. So it's actually even worse than this. I would say today, the best in class would be 4-5 megawatt hour per ton.
Oh, wow.
We're still even way beyond that. So I think theoretically, we will eventually get to something like 1 megawatt hour per ton or something like this. I think that's kind of part of the big race that everybody is in. But at least at scale tech, there's of course always a difference between your lab scale and like when you actually implement the process in real life. But I would say like the at scale processes, which are not nowhere near like the billion tons scale we need. Like in direct air capture, we're still talking in thousands of tons. So 1 million times too small. But already then we're still at like several megawatt hour per ton. So that is indeed a really, really huge challenge. As you pointed out yourself, that's one of the biggest drawback of DAC. Of course, the main thing is we should have avoided emitting all this carbon in the first place, but now we just don't have a choice anymore. So that's just one thing. So all the kind of carbon removal solutions are kind of trying to figure out, okay, what can I do? And there's always a trade-off. So the good thing with DAC, as you said, is like it's very kind of reliable. At least it could be very reliable and very scalable because it also is very compact and very efficient. Of course, that's also why it can scale theoretically to like gigaton scale eventually. But yeah, so that's energy problem is definitely one of them. So we definitely do track this. Like today, it's mostly the megawatt hour per ton that we're tracking. And this is a criteria, I would say that, for example, when you look for investors or when you talk to people that are a bit more deep in the field, they would always want to know like what's your kind of current cost per ton, which is directly linked to this. But of course, that also impacts it's also impacted by the price of electricity, which is a little bit irrelevant. So they will very quickly ask you like, hey, what's your energy kind of requirement? So megawatt hour per ton. So in terms of energy budget, like heat versus the rest. So it of course depends. Some DAC processes, and this is kind of like the more like novel ones, are actually trying to get rid of the heat requirement and go full electricity. So That's, for example, electrochemical systems. So they, instead of heating that part of the process that I mentioned before, where you have to heat up everything to get the CO2 released, you can actually do that different ways. So you can use direct electricity to heat up, or then you can also have a material which has different kind of affinity to CO2 depending on how it's charged or things like this. So you can replace that heat by electricity, but that's theoretically going to also help with the overall electricity budget you will need. But of course, those are still very experimental, I would say. On top of this, from our perspective, what we do is, of course, most of our budget comes from the heat of the cooling tower. So I would say, just to answer you, for our case, we are at easily like 80% of our kind of energy consumption is basically for the heat.
Oh, wow.
It's definitely the largest chunk of everything. And this is also why, in the end, the airflow is an added bonus. Retrofitting the airflow, so kind of leveraging the airflow that's going through the cooling tower, definitely makes sense eventually. But right now we're focusing mostly on like figuring out how to kind of tap into that waste heat in an efficient manner. And also, of course, as always, without disrupting the cooling tower. So yeah, very large chunk of the current system for us is based on the heat and on the waste heat of the cooling tower, ideally. And the reason why we think it's still in many ways better than developing systems, as I mentioned, that would only rely on electricity, for example, even if they're overall lower energy requirements, is because the idea behind those is like, hey, suddenly you have a fully kind of renewable, you can power this by just 100% renewable, and you have basically a completely carbon negative system. But we know that there will be a shortage of renewables for the next decade at the very least. So that means that whatever electricity you use, renewable electricity, you will basically displace something else. So for us, it makes a lot more sense, at least in the next decade or so, probably even 15, 20 years, to just tap into this waste heat that would not be used otherwise. So this is just kind of a trade-off we do. So we're mostly staying on the more kind of proven system of what's called the temperature swing. So using heat as a system for dissolving the CO2, for releasing the CO2, but of course, tapping a lot into heat that would normally just be wasted. So our kind of megawatt hour per ton number is actually, we have two of them. We have one that's the pure process requirements, and then one that's really going to just what we pay for, which is the electricity, and which is just a fraction of what the process actually requires.
It sounds like that could be 20% of what it would require otherwise if you weren't using the waste heat. Yeah,
exactly. That's typically what we're aiming for. So it could be eventually maybe 90% or something like this, because we're also leveraging, for example, heat pumps, which themselves have great efficiencies. I'm not sure how the auditors are familiar with heat pumps, but typically that's one of the big things that people are touting everywhere nowadays as a great way to impact climate change, because you go from something that has at best 100% efficiency, which would be like a heating coil or radiator, and now you go to heat pumps, which suddenly can have 3, 4, 5, or 600% efficiency, which doesn't sound even real, but then it enables you to get like very efficiently and very cheap heat in our case, but also like very carbon light energy as well.
Okay, so it sounds like my 1.2 megawatt number is highly optimistic relative.
I think it's basically like a target. Like once we reach that ballpark of 1 megawatt hour per ton, which hopefully somebody or a few of our companies that are working around the clock to try to get to there, we'll reach, maybe we can say like maybe 2030. I would say 1 megawatt hour per ton. That's maybe something kind of, hopefully we'll get there.
Okay. And then, yeah, like you said, cost per ton is the other metric that people talk about a lot. What do you have models that estimate what your cost per ton can be?
Absolutely. So this is, I would say, unfortunately, and that's one of the a bit tricky things about direct air capture in general, is that you're kind of, everybody knows we have a need for this. Like basically, otherwise we just don't have a way out. But the market doesn't really exist yet. The tech doesn't really exist yet. So the only, let's say, larger player that's actually running is Climeworks, which has like this Orca plant in Iceland, 4,000 tons per year. And as I said, that's like in the thousands of tons per year versus the billions of tons per year we will need to reach. So it's super unclear, basically, how any of this will scale to these very, very, very much larger sizes. So the point is, yeah, we have models like everybody else. It's very important because that's kind of like, you need to prove to yourself and of course also to investors and customers that this is our roadmap, this is what we're expecting, and this is how we're expecting to get there. So for example, the 1 megawatt hour per ton that we are expecting to get there in 2030, as I mentioned. So we have like very detailed model based on kind of like our process of today, what are the improvements we're expecting to make, and trying to quantify those based on kind of early results and things like this. But one of the things is that those are only, for most part, assumptions. So everybody in the field can arbitrarily decide or kind of show you numbers that say like, hey, I will be at 500 kilowatt hours per ton in 2030 or 1.5 megawatt hour per ton in 2030, because it's just Excel sheets in the end. So we have models. You're trying to bring as much confidence you can by having them representing as possible the model you have in real life, but you're always going to have to factor in, okay, we assume that we can get this part 20% better, or we can assume that eventually we don't need that part anymore. And no one knows if that's going to come to reality. So the main thing is, there's models. Everything is based on those models, but they're still models. And it's going to be a kind of learning process to see like, okay, how well do they kind of scale compared to reality? And maybe in a few years, we'll have a bit more adjusted like expectations of, okay, this is what we wanted. This is what actually happened. So maybe we can now have a trend that shows like, okay, this is probably what's going to happen for the next 20 years. And probably we'll see if we can actually have a desired impact or not.
Yeah. So what do the models show though? What do you think is realistic for cost per ton?
So I think as I said, like for us, we're aiming for 1 megawatt hour per ton in 2030. So I think that's basically the ballpark that everybody's aiming for, which translates roughly to $100 to $200 per ton. This is roughly 10 times cheaper than what it is today. So that's why it's extremely ambitious as well. If you look at the average price of carbon removal credits last year, it was 1,100 euros per ton or $1,100 per ton. And so obviously going to $150 per ton in less than 10 years, that's going to be very ambitious. But I think that's what the models are made for. It's like they're assumptions, but what they show you is that with realistic kind of, okay, I can get this part 20% more efficient by doing this and this and this, I get to this like 1 megawatt hour per ton. So I don't have to kind of improve like 1,000x something to get there. So I think that's what the models are for, like just showing that there is a path that is kind of plausible to get to this.
And then what about your business model? Will you be, because you're putting something on existing infrastructure, what kind of agreements do you need to put in place? Who do you partner with to make that happen? And ultimately, who are your customers and how will you make money?
Yeah, very good question. So this is also us being so early, a bit of a moving target, but we have, of course, plans for the different phases of deployment. So initially, and that also is very similar to a lot of other direct air capture companies, I would say, we are targeting utilization customers. So this is basically customers that can use the CO2 directly on site. There's a few reasons why they would be interested in something like this, even though it might be very expensive. I mean, in the beginning, we will have fairly small installations. So let's say in the tens to low hundreds of tons of capture per year. So at that price, at that quantity, prices for kind of commercial CO2 are very high. So that means that even if our DAC CO2 is very high as well, it might still be economically beneficial. But beyond that, even if it isn't, or even if it's kind of like break even, there is still strong incentives for them to do it. Obviously, the emission reduction, that's something that everybody's struggling with. But for example, breweries or any kind of company for which the CO2 is a really core input, if you don't have that CO2, then you don't have a product. So you have to shut down the factory, you have to shut down production. And that's obviously crazy. So one would think that in a current world where it's always talked about how much CO2 we have, too much CO2 and everything, that would not be a problem. But actually, very ironically, we very often have a shortage of commercial CO2. So this is because today, most of the commercial CO2 is actually a byproduct of other productions. So, and it's typically coming from those factories that burn a large amount of natural gas. So from this, you get almost pure CO2 as a byproduct. So you can bottle that and kind of sell it to people who want it. But for example, in the last few years, we had the COVID epidemic that shut down all plants, of course, because there was nobody buying anything. And that meant that CO2 production completely collapsed. And again, last year, with the Ukraine crisis, the prices of natural gases went super high for a few months. And again, that meant that a lot of plants were not profitable anymore with those kind of prices for the natural gas. So they again shut down and again impacting the CO2 supply chain. So there has been a lot of interest from city utilization to have self-reliance in terms of CO2 production. So our kind of offering is very attractive to them in that sense that, okay, you're a factory, you have cooling towers, you are, of course, a bit price sensitive, but if you're kind of like a smaller brewery, you're already paying ridiculous amount for your quantity of CO2 anyway. So you're kind of happy to get, okay, I'll get like more green CO2 that I produce myself. So in those cases, which is kind of, let's say the next 2-3 years, we would sell machines to these companies and they would want ownership. So this is something we actually were quite surprised about. We initially thought that we're going to lease it to them because it's less of risk for them. But it was pretty clear that, no, we want to own this because the whole point is that we want to be self-reliable. So if you lease it and then suddenly you decide, hey, I don't want to maintain this anymore and I take it back, then they're again without anything. So that was quite interesting. And that would be the kind of our go-to-market business model. So really selling those smaller scale machines, focusing on utilization. So we also don't have to figure out just yet the potential logistics and at least sequestration of the CO2. Of course, that also means that we're not relying on carbon removal credits until then. because if you use the CO2, then eventually it goes back to the atmosphere. So you're not really helping. And that also means that it's not our ultimate goal, which would be then, of course, sequestration and mostly relying on removal credits, because that's where you really start having an impact on the climate crisis. And in that front, we do not want to have very large fleet operating, especially globally. So when it comes to internationalization, so this is more the long-term vision. We definitely don't want to kind of have to maintain hundreds or thousands of installations around the world, which needs to be maintained every few years at least. For example, replacing the chemical or at least checking that they work properly. So in that front, we have actually quite a few interested partners. So some of them are more on the kind of cooling tower manufacturers front. Some of them are just large industrial players with whom we have a very good relationship. But in both cases, they would have access to already a very large fleet of global cooling towers. And they would basically be licensing our technology so then they could equip their cooling towers with this kind of system themselves. In the case of cooling tower manufacturer, for example, they already have people. So they have already these large fleets of maintenance people, because cooling towers need to be maintained every few weeks to every few months, depending on the size. So they have already people going there regularly, having very direct connections with the cooling tower owners. So they would be happy to kind of take on that kind of additional service revenue to maintain our carbon capture unit on top of their cooling towers, since they're already going there. So that would be more like the long-term vision. Our customers would then be just licensing our tech and maintaining it and kind of offering it to their own customers. And those would be more like cooling tower manufacturers or large industrial groups, for example.
Okay, that's smart. Yeah, taking advantage of this whole system that's already meant to kind of build, distribute, and maintain these cooling towers and just adding your technology onto it. Gotcha.
I would say like the philosophy of kind of reutilize the existing infrastructure is something we try to apply at every level. You haven't asked me yet, but I can go ahead because I'm assuming you're going to anyway. For example, it also applies to the storage. So typically one question we have is like, okay, you're a fantastic deck company. You have this great opportunity to reduce the energy that you need on top because you're already using this energy that's going to be wasted otherwise. But now you have all this installation all over the place. What do you do with the CO2? And okay, in the utilization case, pretty simple. We just utilize it. But eventually, as I said, we really want to be more in the sequestration kind of industry. And there again, the main point is today, as you probably know, like all the large kind of bodies, whether it's the US, the EU, or even Germany at this point, have pledged to invest and are starting to build these so-called carbon hubs. So they're more or less like CO2 pipelines to kind of trap the point source emissions. So one of the really, really critical things we have to do, and this is also one thing that we definitely say all the time, and that is very important, is that we first and foremost have to reduce emissions. Like doing DEC, if we continue emitting more, and if we continue emitting what we are emitting today, it's completely pointless. Like it's tens of billions of tons that are just a lot cheaper to not emit than to capture again. So to do this, and at this point, it's very critical. So the IPCC, the UN body for climate change, has really said it's a matter of a few years by now when we need to peak emission. Otherwise, we are just going to enter like irreversible path. And that implies that, for example, all the factories that are running everywhere, all these kind of large emitters, we can't shut them down from the next couple of years. But what we could try to do, and I think what we are trying to do is, okay, let's at least kind of capture their emission and put them somewhere. Like, so this point source emission, which as opposed to what we're doing, doesn't remove anything from the atmosphere, but at least it prevents from entering more. And those emit a large amount of CO2 in very low concentration locations, and you just capture that, and then you have to do something with it. So we build this CO2 pipeline from those locations to sequestration sites. And of course, it so happens that those large emitters, well, they're industrial players, meaning they have cooling towers. So then it's basically our idea, again, to reuse the existing infrastructure to basically do our DAC CO2, decentralized, of course, but decentralized around very highly kind of deserved locations with the CO2 pipeline, for example. So at a very low additional cost, again, we can have sequestration and storage for our DAC CO2 on top of the point source CO2.
Right. Okay, so that solves the kind of infrastructure needed to distribute and store it, because that's already going to be built for CCUS,
exactly,
or for carbon capture and storage. Yeah. Ooh, smart. I like it. Let's talk about the hardware and what you're building physically. Can you describe what it looks like and what kind of the main elements of your system are?
Yeah. So right now, we're quite proud because we just finished our second prototype. So of course, we're still in prototyping phase. There's still a lot of research to be done, especially if we want to go to these larger, like more significant tens to hundreds of tons of capture per year. And then you really start to be already in the few players in the world that can reach that scale. So we're not there yet. Like right now, we finished our second prototype. It can capture 5 tons per year. So that means we entered kilo scale for us. Like that means, because 5 tons per year is nominal capacity. So it's basically, if you were to run this prototype 24/7 over a year, then you would get around 5 tons of CO2 per year. Obviously, being that it's a prototype and it's not actually installed on a cooling tower anywhere, it's just there sitting in our office, and we simulate the cooling tower by basically bringing the heat and bringing the airflow ourselves. yeah, we can't capture 5 tons. that would mean somebody would have to be 24/7 looking over it. But we can at least capture a few kilos now in a few days. So that means that we suddenly have started, also opening the valve for real life tests of, hey, we have now DAC CO2 in a somewhat significant quantities. So we can actually start sequestration trials. And we have a few partners, actually, 2 or 3, that are very interested in kind of like, hey guys, as soon as you have a few kilos, just send them over and we'll try to put them in concrete or put them in kind of actually create some methanol out of it or things like this. And that's super exciting. So in terms of hardware, we have this machine, 5 tons per year. It's around 2 by 2 by 1.5 meters. So I have no idea what that would be in US measurements.
6 or 7 feet square by 4 or 5 feet, something like that, 4 feet.
It starts still to be, while it's still a prototype and very small for an industrial machine, for us and for our small team, we're about 10 people today. It's definitely been a massive achievement. So it also weighs 1 ton. So I guess 2,000 pounds roughly when it's kind of fully operating with all the tanks filled in and whatever. So yeah, it starts to be something that we're actually just moving offices next week. And when you have to move something like this around, it starts to have a lot of interesting questions. And the main components are basically like, you obviously have fans. Right now, as I said, we're focusing on kind of having the fans ourselves. And that's probably going to stay like this for quite some time. You have the reactor. So where the magic happens, let's say. So the reactor is, in our case, a big vacuum chamber. So we're using mentioned before, a temperature swing, but it's actually a vacuum temperature swing. So we both change the temperature and the pressure inside our reactor to kind of trigger the necessary reaction for the whole capture process or capture cycle, let's say, to function. So we have a big vacuum chamber, and in there is like our kind of secret sauce. So like the place where the carbon actually gets captured. So you have first a step where the air flows through the chamber and it enters with 0.04% CO2 at the inlet. Then it flows through the chamber and the CO2 gets trapped basically in the chamber. And then at the outside, you get the airflow without the CO2. And then eventually that basically gets saturated. So your chamber has captured as much CO2 as it can. So that's when you enter the second step, which is called desorption. When you close the chamber, then you put the vacuum in, you raise the temperature, and that basically frees the CO2. So you end up with a pure stream of CO2. So 98, 99, or arbitrarily higher if you need. But let's say right now we're more or less at 99% of CO2 coming out. So from 0.04% to 99%. And then you can basically bottle it. So this is what we do now. We start filling those kilo bottles of CO2 and then we can ship those around. Yeah, so those will be the main components. There's, of course, all kinds of pumps and valves and, of course, the vacuum pump I mentioned and all of that. I would say really the core of the machine is definitely this reactor, which is a big vacuum chamber with like a certain arrangement of what we call the stack inside. So there's a certain arrangement of components to allow for the air to flow and also the CO2 to be captured and released as needed.
Are you using steam to transfer the temperature to the sorbent, or how do you do that?
Well, I mean, that's something like I'm not so sure I want to tell too much about.
Oh, yeah.
Let's say it depends. It depends. So we have a few different kind of reactor designs that we're testing out right now. And some of them are leveraging steam as medium to carry the heat out. And some of them are leveraging just hot water. Both of them are very I would say the process is different. So the reactor design, of course, has to be different. And they both have like plus and minuses. So that's why we're considering both at this point. It's still an open question for us, which one will prove more promising based on our constraint and the fact that what we get from the cooling tower, for example.
What's been challenging about the hardware, or do you expect to be challenging as you move forward? Is there something about your system itself or about maybe integrating with the existing cooling towers without impacting their performance? Can you talk a little bit about where you see kind of the technical challenges?
So just because I have to, coming from the software side, hardware has proven hard in general, I would say. Like everybody knows that, but I've discovered in so many different ways what that means. Primarily, I think for us, the main challenge has just been around like supply chain. So you're a startup, you're trying to go fast to do kind of quite flexible and lean iterations and trial, and just getting the right thing decent amount of time is like you really have to kind of beg your suppliers for like, can I please give you money and can you give me this? Because I assume, because that's the only thing that makes sense, is that you're such a small player that they don't want to be bothered with you. So they really don't want to do because it's a very manual process. So that would mean like, I have to spend a bit of time to get a bit of money. I'd rather spend a lot of time getting a lot of money. And you really have to kind of work a lot on that.
So what do you see the big challenges are to scaling your system? So, and I guess what level do you expect or do you think is realistic to scale it to? We talk about gigatons of removal per year by 2050, and that's just at this point almost an unfathomable scale. But what do you think is realistic for NeoCarbon, and what are the big challenges to get there?
So first, I want to address this gigaton scale by 2050. It's definitely one of the benchmarks that has been used. I think it's already kind of starting to shift to something a bit more reasonable, but still it's, I would say, still one of the benchmark that for investors, for example, if I want to invest in a climate tech company and especially in a CDR company, I want to see the gigaton potential. And I always like nowadays to put this into perspective into like the largest emitters in the world today. And it's infinitely easier to emit CO2 than to capture CO2. Like you basically have to burn stuff and that's pretty easy to do. Largest emitters today, like the ExxonMobil of this world, like these infathomably big companies, they don't emit 1 gigaton of CO2, not even close. They're like already pretty bad. And of course, it's not 1 gigaton. 1 gigaton is enormous. So I have very little, personally, I have a lot of doubt that any single company will ever reach 1 gigaton of removal per year. That's just so enormous. It would be like, something like 10 or even more ExxonMobil. It's like, that just can't really happen, I believe. But regardless, in terms of kind of pure potential, like, yes, if we take, for example, the waste heat market, there is enough heat right now that is purely blown into the atmosphere that we could use to leverage several gigatons of removal. So theoretically, that scales pretty well. What we're saying, somewhat more reasonable manner, although it's also very aggressive, is that we want to reach megaton scale by 2030. So this would be like 1 million tons per year by 2030, which obviously is also very, very big. So that means we, and all the other companies that also think they can reach that would basically scale the whole industry by 1,000 times in about 7 years. So that's fairly unprecedented, I would say, maybe even in software kind of growth. But regardless, that's at least the ambition. So let's see how much we can reach of that.
And you'd need 1,000 companies doing that to get to a gigaton.
To a gigaton. Yeah, exactly. And actually, so right now, the estimates are about 6 gigatons per year that will need to be removed by 2050. But that also implies that we need to reduce emissions basically right now, which we're certainly not doing. So I tend to think that those estimates are themselves very optimistic. So we probably will end up in the tens of gigatons per year. And even after that, until 2000, it might even reach like 100 gigatons per year. So you would then need 100,000 companies like this to get this. This is really I think I'm already kind of dabbling into one of your questions about how optimistic and pessimistic I am. But when you start putting numbers like this into perspective, it's very hard to be like, okay, how are we going to get there? But yeah, we can get back to that in a second, because about the challenges of like scaling. So for us, obviously, it's really about like building ridiculous amount of these plants in a very, very short time. Like time is really of the essence here. It's a tech that's basically not really proven. So you have to really challenge the whole kind of development versus research versus kind of like, let's just put it out there and kind of figure it out while we're building it approach, which obviously is very risky. So I would say that's not just for us, but for DAC in general, this challenge is how do you scale at this insane rate a tech that is very little unproven and also needs to be improved immensely. So you both have to scale and improve at the same time. And one of which would already be pretty challenging, but now you need to both at the same time. So that's definitely like on the scaling side, something that's I'm already seeing this, we're only 18 months old and we're already kind of having to make decisions between, okay, do we commit more resources to starting to install some of those things so we get a bit of kind of learning from the fields, or do we try to scale this internally, like try to build bigger machines that actually work and we then just sell those? And when you have this kind of exponential progression, it's always a very difficult call, because you can be like, okay, I could build 10 tons machine this year, but if I wait a year, I could then build 100 tons machine, which would kind of balance, but then I could build those 100 tons machine. But then of course, when you're at the 100 ton machine, you'll be like, okay, instead of 100 ton, I can wait one more year and then I do 1,000 ton machine, and then you never do anything. So it's very kind of like, when do you put the button of, okay, this is big enough, this is kind of efficient enough, and when you're like, okay, I still really want to get this cost lower. So that scaling versus improvement is going to be key.
Yeah, I think that's something a lot of companies in this space are struggling with, and you've articulated it really well. Okay, cool. So I have a few last closing questions, and you touched on this a second ago. How optimistic or pessimistic are you about the future of our planet, and why?
So I guess I wear a couple hats on this one. So as I briefly talked about before, my kind of like really engineer hat, really like scientist, I would say, even like that likes to look at the numbers and play like back of the envelope kind of approaches. It's like, it's hard to be optimistic when you look at these numbers. CO2 is only one of the many problems we have. There's also like methane problem. There's like biodiversity collapsing. There's water crisis, all kinds of like deforestation. There's really a lot of these really big challenges. And you pick any one of them, for example, CO2, and you get very quickly into those things like, hey, to get to something that would be quite good, but not even perfect, but at least quite good, you need the industry to grow like 10,000% per year for the next 50 years in a way that just hasn't been made by any other industry before, in a way that's using tech that's unproven and everything like this. So that side of me, definitely a bit more skeptical, maybe not pessimistic, but at least skeptical. But of course, I think that's part of the entrepreneur personality. I'm an irrational optimist. I like to put it like this. So then I just have to believe. It's like, what else can we do? You look at this, you're like, okay, we have right now a very bad chance, I would say. But first of all, it's been in the past many times that suddenly out of nowhere, like an opportunity arose. And if something, changes drastically, I don't know, I'm throwing some random idea. I don't think that's going to be the key, but let's say AI suddenly like brings, okay, this is what we do, what we can do to really fix this problem. Then we need to be ready. We need to be like, okay, good thing that we spent the last 10 years kind of fighting our way to something, because at least we're not where we were 10 years ago. So the chance that something kind of clicks and really helps us solve for good our problem will only happen if we try anyway. So that's kind of my optimism is you don't really have a choice. Like doing nothing is for sure not going to help. Let's do the best we can. And there is always a chance that something will kind of unforeseen make it work out. So that I would say in that sense, I'm quite optimistic. I want to believe. I definitely spend most of my waking hours thinking about this and working on this. So of course I wouldn't do it if I was purely kind of thinking like, hey, this is pointless. So I would say a bit of two hats, but trying to keep at least when I'm working, the more like optimistic hat on.
Yeah, that's a great answer. And somebody I was talking to the other day mentioned that kind of breakthrough concept as well. And it's happened before, right? Like I think they mentioned that mapping the human genome went way faster than anybody ever possibly believed it could.
No, exactly. And I mean, it's a bit sad that we probably will have to hope and rely on something like this to happen. But at least that's what we have now. We have optimistic outcomes that still might work out. So I guess that's what we need to hang on to.
Who is one other person or company doing something to address climate change today that's inspiring you?
Yeah, so that was a very good question. When you mentioned you will ask this, I really thought a little bit like, okay, for me, it's just so important at this point, as you said, like if you do a bit the math, we're going to need thousands of companies and thousands of approach because we also don't know which one will work or not. I really want to say like always anyone I meet that's kind of hesitating or doing whatever they can in whatever way, I'm like, okay, this is great. So that's the kind of shout out I first want to say, like everybody out there that's just trying in their own way, at their own pace, at their own scale to do something a little bit better than they did yesterday. I think that's amazing. More specifically, I think one person that's been super impressive and definitely very helpful, and we have had a few dealings with him as well. So it's Robert Hoglund, which you've probably heard. So I think he's single-handedly, so he's Swedish. He's been very close to the Swedish government, and he's one of the reasons why Sweden is ahead of pretty much everybody else in terms of like emission reduction policies and CDR and everything. But yeah, so he's single-handedly, or at least he's been the face of that effort, kind of made very transparent CDR efforts, kind of formalized where are we today, what do we still need to happen, kind of like put that. A lot of people are working on something that is very risky, very long-term. And it was a very big mess of like, okay, maybe not is working, we don't know. And trying to put some structure, some transparency in this has been one of his great achievements, I would say. So there's, for example, CDR.FYI. So anybody can go there and see like all the recent carbon removal purchases. And yeah.
Oh, he's behind CDR.FYI?
Yeah.
Oh, yeah. I'm embarrassed. I know of that. I'm embarrassed to say I didn't know about him. So I'm going to have to go look him up.
Nice. Well, I mean, that's why I'm shouting out to him. Like, I think he's an amazing guy. And for sure, he's not working alone, but at least he's, as far as I know, the face of all of these efforts. So.
Awesome. What advice do you have for someone who isn't working in climate today, but wants to do something to help?
Well, I would say just do it, first of all. I mean, as I said, I'm a very big believer that I've been trying my whole life to be a little bit better, and I'm still not perfect. I try to, like, this personal life sustainability things that I did. The ones that are very famous are like the 4 kind of ways you can really mitigate your own impact is kind of adopt a vegetarian or vegan diet, don't own a car, don't fly with a plane, and more controversial, don't have kids. I did this as much as I can. And I'm here this week, actually, I'm in Finland. So yeah, I had to take the plane. I'm trying to limit that as much as possible. But having living almost 10 years here, my girlfriend's family is here, everybody has reasons. So of course, you need to think about those and weigh the pros and cons. But I would say like anything helps. And so just do it. If you have a crazy idea, and especially if you have a crazy idea, you should definitely pursue it. How to do it is reach out, for example, to me or other people in the community. I think one of the best things about the community of the CDR and climate tech is that most people are in it for the impact, for really like not building like company building or not making money, but really like, hey, I'm really worried about this. I want to try to do something. I want to jump on that train of like, I'm tired of seeing politicians or whatever taking too long. And that means that it's a massively helpful community. So people are really open to exchange and it's very easy to reach out. So I would say that's, if you're a little bit kind of unsure, like, how should I do this? What should I do? Should I do it at all? Yes, probably the answer is yes. And if you want to build up confidence, just reach out. So you have all this, on the CDR side, you have all this community, like for example, Air Miners, where you can like meet a lot of fantastic people. There's more and more kind of conferences around the world, like Slack, Discord groups that are really focused on impact on climate at personal level, company level, building startups. On Reddit, there's also a lot of things as well, for sure. So I would say like, get in there and don't feel crazy. Like we need crazy. We really need crazy at this point.
Cool. I love that. I've found that about the community too. Silvain, that was really fun. Thank you for all your time and for what you're doing. I think you're taking a really practical approach to everything with a bit of craziness too, which is good. I really appreciate it.
No, thank you. Thank you for having me. It was super nice and a pleasure to discuss. And I hope if this can inspire anybody to take the jump, that would be my good deed for the day.
Awesome. Thank you.
Thanks.
Hardware to Save a Planet is brought to you by Synapse. To find out more about us and how we develop hardware solutions for the world's most ambitious companies, head to synapse.com. And then make sure to search for Hardware to Save a Planet in Apple Podcasts, Spotify, and Google Podcasts, or anywhere you like to listen. Make sure to click subscribe so you don't miss any future episodes. On behalf of the team here at Synapse, thanks for listening.